The work done to move a charge from point A to B. Okay, so we have this is our source charge, let's say, and this is our test charge. The source charge is the one that gives us the electric field, whereas the test charge is something that we move towards the source charge or away from the source charge. Depends on the question. Okay, so when we move a charge from point A, we have seen this, point A to point B, we need to do work, but we don't know if the work is supposed to be positive or it is supposed to be negative. So this is where our equation comes in. So work done, we know that it is equal to minus delta PE. What is delta PE? Delta PE is the change associated with the change of potential energy associated to the test charge. So we are talking about the test charge that we are moving, not the source charge. We're not changing the potential energy of the source charge. We are changing this dude because we are moving it up away or towards. When we move something, there is going to be a change. And what change is that? It's called the potential energy. And work done to move from point A to point B is equal to the negative of the change in potential energy. So let's say if the charge gains, positive and gains potential energy, so that's a positive potential energy, which means that the work done is to move it from point A to point B is going to be a negative, and vice versa. Kalau potential energy decrease for that charge, then the work done is going to, then the work done is going to be positive. So we have this equation, W equals to minus delta PE, and we use it a lot, many times in different forms. Okay, so we know that delta PE is equal to minus QEX delta X. And what does the X represent? This guy is an X, this guy is also an X, which means that they need to be parallel. Parallel means selari. Kalau this is my E, this is my delta X. Yes, this works. If my E is this way and my delta X is this way, yes, it works because they are still in parallel, but the directions are different. If they have the same direction, both are to the right, then this component will be positive. If they are both going to the left, this component will still be a positive because they are in the same direction. If they are in opposite direction, tak kisahlah E to the right, E to the left, and your displacement is opposite of what E is, then this component will be negative. Okay, so yang penting to use this equation, your E and your delta X must be parallel. This equation will not hold if they are not parallel. So you need to use another equation if your E is not parallel to your delta X. Okay, so there is another equation. If you guys have forgotten, hope you guys have not forgotten because baru lagi belajar. Okay, so let me kemaskan kejap. Oh, I want that. Okay. There's another equation for delta PE or W. Let's go for the W because W is more easier to remember because it's weird. So K, Q, Q, if I'm remembering this correctly, and I told you it looks like a delta, but it's not really a delta. So it's 1 over R initial, yes, R initial minus R final or RA to RB, which is terbalik lah kan. Selalunya delta is final minus initial. Here we start with A and minus with a B, which means that we go from initial to final, terbalik. So this guy is not really delta, but it looks like a delta, but it's not, so it's weird. So you guys, this is the tip to remember it, it's weird, okay? So the work done to move it from A to B is a weird equation because it looks like a delta, but it's not really a delta. Okay, so with that said, I know what is W, which means that I will know what is my delta PE using this equation. So I just need to put in a negative sign over here, or I can just flip this guy over here, 1 over RB minus 1 over RA. So you will get the inverse, you will get the negative of work. So that is work and delta PE. And okay, we can use this equation for positive charge or negative charge, and this equation will hold. If I have a positive charge, then my delta PE is a negative. If I have a negative charge, then it will be a positive. Okay, assuming that this component is a positive lah. Okay, so you know how to use that equation. We've seen it. Then we talked about potential and equipotential lines. New slide. So we talked about potential, and I said, okay, potential is actually when you have a charge from infinity and you want to move it to a point called R. So this is your point R. What is point R? It is the distance towards your source charge. So pendek kata, wow, my BM is cemerlang. So this is the radius to that point. Okay, so this is also R, right? So I can bring my charge to here, sama je. It will still be R because it is the radius. So R is a point away from the source charge. So we don't know, it depends on the question what R is. Okay, so that is potential is bringing the charge from infinity to point R, and it is equal to the minus work done over, what was it, Q good, to bring a unit charge. I think so. Sekejap, let me check. So V.
Betul.
Betul. Okay, V KQ over R. Okay. Betul. Thank you. Betul. Where is my recap? Okay, so that is your equation. And there is another form for potential energy, which is KQ over R. What is Q? This is associated with the source charge. Okay, because this guy is just your test charge. Potential is always related to source. Okay, so K is your constant, Q is your source charge, R is the distance from the source charge. So what does this equation tell you? It tells you, hey, what's the V around the source charge at this point? So, and we also have learned that going towards the charge, we get a higher potential. And going away, we get a lower potential. And we also have seen the case where the source charge is a negative. Going towards the negative source charge will give you a lower potential, and going away from the negative source charge will give you a higher potential because it becomes less negative. Okay, so going back to this equation, I said, okay, so this equation tells us what the potential at a particular point is. So if I want to know, okay, what is the potential at this point? I want to just stand over here and I say, okay, what's the potential over here? What am I going to feel over here? There's a source charge, there's a big, huge source charge at the center, and I want to know, hey, what's the potential that I'm feeling? So this is Umar and this is me, right? So Umar feels, let's say he feels 10 volt. Pretty good. So I'm away from the source charge, I'm further away, which means that I will feel a lower or a higher potential.
Lower.
Lower, right? I'm away from the source charge, which means that I will feel something lower. Let's say it's 5 volt. And how do I calculate specifically what is the value? I use this equation, KQ over R. So if Umar is like 1 meter away and I am 2 meters away, our V is different by the R. Umar will use a radius of 1. I will use an R of 2. So that makes my V smaller. Okay, so V, and then what else? Equipotential. We already talked about equipotential. So this is me and this is Shasha. I feel 5 volts. Shasha will also feel 5 volt. What is that called? It's called equipotential. Around the same radius, we will feel the same potential. We will feel the same potential. So equal potential is just equal, feeling equal potential, which is V. Okay, if Umar is here, Fakri is here, who else? Ishraf is here. So Ishraf, Fakri, Umar feels the same potential, which is 10 volt. Okay, so that equation tells us that to macam kalau kita nak kira pakai equation lah, if like conceptually that is how it is. Okay, oh, I forgot about this equation. Oh, this is the next subtopic that we talked about briefly yesterday. Wait, nak check jap. Okay, V is scalar. We have not talked about that yet. So new slide. So we talked about V, we talked about equipotential, and now if I have like a setup, let's say it's a square. Okay, so this is a square. I have 3 charges over here, and I'm just like menyibuk kan. This is me. I'm just like, I just want to stay here. Okay, so I want to know what am I going to feel from these charges. So this charge is like 5 microcoulomb, don't know, maybe 10 microcoulomb negative, and positive 7 microcoulomb. And I want to know, okay, what am I going to feel if I stepped on that dot, right? So to know what the potential that I will feel at that particular point, I need to know what is the contribution by each charge. So this one, possibly V1, I'm just going to label that as V1. This guy is V2. This guy is V3. So how do I calculate for V? V is KQ over R. K is just a constant. Q is referring to the charge that is giving me the effect. And R is the distance away from the charge to that point that we are looking for. Distance from charge to point. Okay. So now that I know what is V1, I know what is V2, I know what is V3, I can know what is V net, which is what I'm feeling. So V net is equal to the net V's that I am feeling, which is just adding V1, V2, V3 together. Or if you don't want to calculate it separately, you can just say, okay, KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. Q1 is different than Q2, Q2 is different than Q3, R should be equal distance je lah. Okay, so you need to take care, if you are going to use this equation, you need to know what charge and what is the distance. Jangan mess that up lah. Okay. So that is V. V is a scalar quantity, does not have positive or negative direction, which means that the signs here, you need to put it inside this equation. So positive, this guy is positive. This guy is a negative, so it's a negative sign over here, positive. Okay, so I told you it's a scalar quantity whereby it does not have a direction, which is a positive or negative, but I just put in positive or negative. How do I say this? So scalar quantities cannot be resolved into the x and y components. Okay, when we have a vector, we can resolve it into x and y components, and this is what I mean by going to the going positive or negative. Going up is positive, going down is negative. So that is related to vectors. For scalar, the positive just means it has a positive charge. It just means that. It does not mean it's going to the right. It doesn't mean it's going up. It just means it's a positive. So that is why it's called a scalar. Okay, it's not related to direction. It's just related to the charge. Okay, that's clear. Okay, what else did I miss? I think that's it. Oh, we also have equal potential surfaces, which is just the same as equal potential lines. I think it's a pretty easy concept for you to understand. Okay. Released from rest, positive charges accelerate spontaneously from region of high to low. Okay, so because high potential is associated with positive, low potential is associated with negative, which means that positive is always going to be attracted to negative, and it means that it will be going to the low. And then vice versa for negative. I think that's also easy to remember. It's kind of intuitive. Next. Okay, I think that's it. We are good. So we can continue. What time is it? It's 10:20. Lamanya recap. How many people do we have now? We have 34. Okay. Oh, one more thing I forgot. Coulomb's force is a conservative force. We're talking about Coulomb's force. Yeah. So the change in kinetic energy plus the change in potential energy will be equal to 0. Remember, if I'm gaining potential, I will lose kinetic. If I'm gaining kinetic, I will lose potential. If I go from rest to a certain speed, it means that I'm gaining potential, which means that my PE will go down, okay, and vice versa. So this is the very, very important equation to remember, okay. I think 1 over 2 mv squared, you know this already, you know what is PE, just remembering the equation and using it correctly. Okay, so I hope that was helpful. I know it's a lot, but it is what it is. So we have seen this one. This is a new one, potential energy PE or U. Previously, we talked about delta PE. So this is PE of a pair of charges as QV. Okay, so it's the charge multiplied with the V. Remember, I told you V is associated with the source charge, whereas this small q is your test charge. So this is your source charge, the capital Q, test charge, your small q. So when you are multiplying q with capital V, which is potential, you are actually multiplying with the source charge, which is kq over r. Okay, so that's another equation that kita baru sangat tengok. Okay, we know this equation already. Okay, let me just go over this quickly. So work done by the electric force with the same direction to move the charge from A to B. So this is a positive charge. It's going from A to B towards a positive source charge. So using the equation that we have learned from the beginning of this subtopic, WAB, KQQ, test charge, source charge, A is the initial point, B is the final point. So RA is at a further distance than RB. So RA is a further distance than RB, which means that this component, this 1 over RA, will be smaller than 1 over RB. When we have something smaller minus with something bigger, we will have a negative, which means that our work is a negative work. Negative work means you are doing work against the direction of force exerted on charge positive Q. Now remember, your positive charge, this is a positive test charge and this is a positive source charge. They don't want to be together. They are going to repel each other, which means that naturally this guy will want to move away. So this is your F lah. This is your F. So when you are trying to move it from point A to point B, you are actually forcing it to go against the force, forcing it to go against its natural direction. So that is why it's a negative work. Okay, remember work equals to force times distance. If they should be parallel, but if they are in the different direction, then you will get a negative work. We have learned that last semester. We are just applying it again in this chapter for electricity. Okay, and the same case for this guy. Okay, let's do this intuitively. I have a positive and a positive, which means that I am going to be repelling each other, not me, the charge. So the charge is going to be repelling each other. So this is the direction of the force. I want to move it from A to B. The work done is following the force. The displacement is also following the force, which means that I should be getting a positive work. So RA is less than RB. RA is bigger minus something smaller, which means that I will get a positive over here. This gets a positive work done. So it's correct. Intuitively, it's correct. And when we calculate it, that is the answer. Okay, there is no work done when we move across a same equipotential because it's the same voltage. Same voltage means same potential energy. Sorry, same potential means also same potential energy. Let me write that down because it's kind of confusing. Same potential is also same potential energy. Okay, because PE is made up of potential. PE is QV. If V does not change, QV does not change. Okay, okay, and when we move a positive charge towards this guy, we are moving it towards a higher potential. We are moving it towards a higher potential. So this guy will have a gain in PE. Remember, gain in PE equals to a negative work done. Cos minus delta PE. So if I'm gaining PE, it's a negative W. If I'm losing PE, it's a positive W. Okay. I think by now, dah okay kot. Kita dah ulang-ulang balik dah the concept of it. Okay, so let me ask about this one. Okay. Saya nak panggil siapa hari ni? Nak panggil Anis. Is Anis here? Is Anis here or is she away?
Yes, Doktor.
Okay.
Saya.
So
Tak,
Anis.
saya ada.
Okay. So Anis, I'm going to ask you. Okay. So we have a positive Q test charge and we have a negative source charge. Are they going to be attracted or are they going to be repelled? This diagram.
Macam mana, Doktor? Satu
Okay. So
positif, satu
dengan
negatif.
repel ke attract? Oops.
Repel.
So it's going to be repel. Repel. Positive dengan negatif. Sure.
Attract.
Attract. Okay, so they are going to be attracted. So my force will go this way. And I want to bring my test charge from point A to point B. So the displacement is in this direction. What should be my work done? Is it a positive or a negative? Okay, I'm going to give you a hint. Work done is equal to the dot product of F and delta X, where both are vectors. So they are in the same direction. Should my work done be positive or negative?
Positif.
Positive, because they are in the same direction. Thank you, Anis. That was good. So they need to be in the same direction for this equation to be positive. So here we see it's a positive. Okay, senang je sebenarnya. Just have to like fikir sikit. Okay, or you can just use the equation. But if you mess up your calculation and you don't know how to look at this diagram like how I told you, then you won't be able to check it, right? So knowing both of these is equally important. So now this guy is a positive with a negative. The force is going to be attracted. I mean, the test charge is going to be attracted. So the force is going towards the source charge. And I want to bring my test charge from point A to point B, which is delta X going away from the source charge. So they are parallel, but they are not in the same direction. So W equals to F dot delta X. This is a vector. Vector, remember dot product, they have to be parallel. But if they are not in the same direction, it's going to be a negative. So this is a negative work done. You don't have to memorize this. I'm just telling this equation to you in case it helps to understand this better. You just need to know it should be in the same direction for positive work done. Okay, so this is different one. I think we're good. Okay, so moving on to energy unit. The work done on a charged particle in an electric potential can be in the form of WAB equals to minus delta PE or equals to minus Q delta V. We have also seen PE or U equals to QV. Okay, so we have seen this. So if I wanted to put in a delta over here or delta PE, if I have a delta over here, I need to balance it out by having another delta on the right. So remember, PE is not the same as delta PE. PE is not the same as delta PE. This delta means everything. If you don't have the delta, it means a different thing. So if I have a PE and this is the equation, if I want to make it delta PE, I need to put in the delta somewhere. So the only possible place to put the delta here is at the V, because I am moving my charge. I am using the same charge. I'm not changing charges. So I can't change that. So the only possible place to put in the delta is next to the V. So the change in potential. Remember, kalau ada delta, your right hand side should always have a delta as well. Kalau tak salah. Okay, mathematically is wrong. Physics wise is also wrong. So actually physics is like math in disguise a little bit lah. Okay, I don't like math either, but we have to deal with it. So electric potential. Okay, so we have an example. Let's just look at the solution terus because we are out of time. The electric potential at a certain point of space is 12 volt. So so remember, if we have like potential, it means that we have a source charge somewhere. This is a positive potential, which means that my source charge should be positive. So at some point in space, it's 12 volt. So this is along this line, along this equipotential line, it's 12 volt. So what is the electric potential energy? So it's asking PE. What is the electric potential energy of a minus 3 microcoulomb charge placed at that point? So I have a negative source charge. Sorry, I have a negative test charge. I have a negative charge. I can't say test charge. Test charge always means positive. So minus 3 microcoulomb. PE equation is equal to QV. Do I have all the information to solve this? I have Q, which is minus 3 microcoulomb. I have V, so I have everything. Minus 3 times 10 to the minus 6 times with 12. So that is my PE. What is the unit for PE? PE is a type of energy, so it is in joules. Okay, this is pretty easy. You just have to draw the diagram. It helps me, so I think it should help you as well to draw it. So jangan malas untuk lukis, because it helps your understanding. Okay, next one. Banyak lagi ke? Okay. If the work required to move a positive 0.35 coulomb charge from point A to point B is positive 1 to 5. Okay, so we have work done is 1 to 5. Okay, so that is the first information. We are trying to move positive 0.35. So this is the charge and from point A to point B. Okay, this is my charge. I'm moving it from point A to point B and the work done to move it is positive. Remember, if I have a positive work done, it means that I will have a negative change in potential energy. Okay, so that is a hint over there. Positive work done means negative change in potential energy. And then I want to know what is the potential difference. What is potential difference? Difference is delta, potential is V. So I'm actually I want to find delta V. So I have delta PE over here. Delta PE is equal to delta V times Q delta V. We have seen this in earlier slides. I know this information, which means that it just means my delta PE is equal to minus 125 joules. Okay, based on this equation, work done is 125, PE is saya terlupa, minus 125 joules. Okay, and then I want to know what is delta V. I know what charge I'm looking at, which is a 0.35. So just substitute that in here. And delta V equals to minus 125. So delta V is this guy. Yay, tak pakai calculator. Okay, so the trick to this is just remembering the equation. Okay, it's not really hard, but it gets hard if you don't remember. Okay, any questions so far? I think I'm going pretty fast because I want to finish this. But if I'm going too fast and you don't understand and you want me to repeat some points, you can. Just interrupt me. Okay, I hope you're not sleeping. Okay, next one. A charge Q1 is minus 5 microcoulomb. Okay, a charge Q1 minus 5 microcoulomb is stationary. Stationary means at rest or V equals to 0, V initial. Another charge Q2 equals to 4 microcoulomb moves from a position of 0.16 from Q1 to a position of 0.28. So it's saying that Q1 is at a point 0.16 and then it moves to a position of 0.28. Okay, so it's actually moving by, yeah. Okay, sorry about that. So 0.28 minus 0.16 is 0. Macam kat mana? So 0.12. Okay, so what is the potential energy change experienced by Q2? Does Q2 gain or lose potential energy? Okay, so if I want to look at this intuitively, right? I'm not going for the calculations yet. So I have a positive charge and I'm moving away from a negative charge. Supposedly this is my source charge because the source, that guy is not moving, right? And this guy is moving. So I'm going away from a negative charge, which means that I'm going towards a higher potential, right? In another example, if I have a positive charge and this is my positive charge, I'm moving this away, I'm going to a lower potential because this is associated with high. This is associated with high potential. Moving away means I'm going to a lower place. This guy is associated with low potential. If I'm moving away from low potential, I'm going towards higher potential, right? So my delta PE should be a positive. Okay, so that is looking at it just conceptually. Okay, so now let's look at the equation. So delta, what is the potential energy change experienced by Q2? So delta PE is UF minus UI, or final potential energy minus initial potential energy. We know that we have different equations for PE, which is QV, or PE can be K, Q, what is, there's so many distractions. Okay, V is K capital Q over R, if I'm remembering this correctly. Okay, so we can use either equation. So UF is KQ1 Q2 over RF minus KQ1 Q2 over R initial. Okay, so we have a delta here, which means that it's going to be final minus initial. Okay, so just we factor this out because they are the same. And then we are left with 1 over RF minus 1 over RI. So just plug that in. K is 9 times 10 to the 9. Your Q1 is minus 5 micro. So that's times 10 to the minus 6. Q2 is 4 times 10 to the minus 6. Then your R final is the final position, which is at 0.28. And your Ri is 0.16. Okay, so just use the equation. If this was like, if this was a hassle for you, there's another way to do it, which is just remembering that WAB is KQ1, KQQ 1 over RA minus 1 over RB. This is initial minus final, which is also equal to a minus delta PE. Okay, so here we see the answer is a positive 0.48. The charge Q2 gain potential energy, which is a positive, which is our intuition was right. Okay, conceptually, we were right before we even solved it. So that's how you check your answer. Right. Okay, so charged particle in a uniform electric field. We have seen this case where we have a positive charge. We will want to go to a low potential. That's lower. And if we have a negative charge, we will want to go to a high potential or a positive. Don't know what's wrong with my tablet today. High. Okay. And we also know that this is equal potential lines. Okay, bayangkan to equipotential. So remember we talked about equipotential and we talked about a single charge. And this was our equipotential. So that was for a single charge. So you get a circle. This guy is like a whole pembaris, right? Pembaris of positive charges. So your equipotential should be in a straight line as well instead of circles. So it kind of makes sense, right? So if your charge wants to look like a square, you would have square equipotential, right? So it depends on the shape of your charge, how they are arranged. So dapat, kalau ada pembaris, you get a pembaris equipotential. What does it mean? It means that this V1, this is V2, this is V3, and V3 is at a lower potential than V1. You know how to calculate for V. V is KQ over R. The further away you are from the source charge, the lower your V, etc. Okay. Ini apa beza dengan atas ni? Sekejap. Okay, so it's perkataan ni berbeza. So when placed within the electric field, a charged particle will experience a force parallel to the field and accelerates in the direction of the force that acts on it. Okay, so remember E should always go from positive to negative, from high to low. That's your electric field. Your force depends on whether you are attracted or whether you are being repelled. So positive is attracted to negative, so your force is to the right. Here your force is in the same direction as your E. And then this guy is attracted to positive, so this is direction of force. It is in the opposite direction of the electric field applied by the pembaris. Okay, so it's different than the one that we talked about. It's different than the one that we talked about. I said your E is in the same direction as F. To a different case. How do I say this? Okay, so we have a positive and this is a negative, and they will want to be attracted. So this is your E. Okay, so that's your E direction is that way. Your force direction is also in the same direction. So that is what I mean when your E and F are in the same direction, even though their equation are different. Remember, F is KQQ over R squared. E is what? KQ to bring unit charge. So it's KQ over R squared. So the equation is different, but the vector direction is the same. This was when we had like two charges situation. Here, this is not two charges. This is pembaris, and charge. So it's different. So the electric field is applied by the pembaris or the bar. What's a bar in Malay? Bar. Tak tahulah, pembaris je lah. So pembaris ni dia apply electric field, and the charge that you put within the pembaris feels that electric field. So sekarang ni we don't have a source charge. We have like pembaris source charge. So it's different. So your electric field is applied by the pembaris Whatever charge you put inside will feel the electric field. Okay, and the force depends on the charge that you put inside. Okay, so I hope that's clear. The distinction between what we have talked earlier versus this one. And then we know that F equals to QE. We talked about this in the first subtopic where Q, what is wrong with my pen? Or am I writing too fast for this guy? Q over R squared. E is QE, which is KQ over R squared. Okay, need first subtopic if you guys don't remember. So this is our equation. We also know that force is equal to MA, right? This is like the typical equation. This is Newton's second law. First law, third law. Third law is opposite equal. First law is inertia. Second law, yep. This is the second law, F equals to MA. So A is QE over mass. What mass? Mass of the charge. So if you have A, you can find V using this equation. Okay, I know like, tolonglah nak kena belajar ni balik. But yes, you have learned this one, just apply it. You have A, you can put it inside this equation, assuming that it is at rest, U is equal to 0. You know the S, the displacement, you know the acceleration, you can solve for V. Or it is equal to 2 QE over M times D. Basically just applying, okay? I think they should be okay for you. And we have also talked about this. W equals to minus delta U or delta PE is equal to delta K. Positive delta K means negative delta PE. Again, in kinetic energy means you are losing potential energy, vice versa. Okay. So kita basically this subtopic is a recap and a lot of applying equations into another equation, which is a hassle, but I believe it's important to connect everything. Okay, and then we have charged particle in uniform electric field. Uniform electric field applied by the pembaris. Why is it uniform? Because your pembaris does not move. It's just stationary there, and they are applying constant electric field. So when you put in a negative charge and a positive charge, secara melintang, secara perpendicular, put it like that. Melintang means perpendicular ke? Not sure. So going like that. So this dude is obviously attracted to the positive, right? So it will accelerate towards the positive. And then positive dude will accelerate towards the negative pembaris. That is kind of intuitive. You don't have to memorize that. Okay, I think we are done. Yes, we are done. Tinggal satu soalan je. Yay. We have 12 minutes. Let's do this fast. Okay. So I'm going to try my best to write this nicely. So two positive charges, a negative and a negative charge, each of equal magnitude. So we have, they are arranged in equilateral triangle. Equilateral means semua side sama kot. I think that is what it is. So this is, we have three charges. One is positive, two is positive, one is negative, sorry. Two is positive, 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 and this is negative. Each of equal magnitude 2 nanocoulomb. Okay. So semua sama, sign lain-lain. With side of 10 centimeter. Okay, so let me write that. So this is 10 centimeter. Wow, cantik lah tulisan saya. Points M and N are respectively the midpoints between the two positive charges. So M is between two positive charges. Point M and N are respectively the midpoints between two positive charges and between the positive and negative charges. Okay, dia cakap satu M, satu N. M yang pertama, M tu which is the midpoint between the two positive charges. So positive dengan positive, this guy is your M. Okay, and then your N is between positive and negative. So it could be here or it could be here. So tak kisah, sama je kot I think. Let's just try. Calculate the electric potential at M and the electric potential at N. Okay, I want someone to do this for me. So Ya Allah. I am so sorry. Okay, potential at M, I want, let me see the list. Sorry, I know it's the last, like, I know it's like the last few minutes of class, but this is very important. Okay, can I get Shakira to do, hello, can I get Shakira to do A? Okay, the electric potential at M, what is electric potential? It's V. Okay, if you guys remember what is V equation. So Shakira will be doing that. Christina will be doing B. The electric potential at N. C, I want, can I get Redha? Lama tak dengar suara Redha. Can I get Redha to do C? Oops. And D, I want, oh, Haikal. I want Haikal to do D, eh? Okay, jap, let me write that down before I forget. So Shakira is the first one. Shakira. Second one was, siapa tadi? Forgot already. I remember Redha doing this one. This is Haikal. Siapa lagi seorang tadi? Was it Christina? Yes, Christina. Okay, and last one. Lucky winner is Fairuz. Fairuz, macam tak pernah panggil je Fairuz ni. Okay, I want you guys to do this and then please share your answer with class. Boleh? Is that okay with everyone? Am I not hearing anything?
Okay.
Okay. All right. So I'm going to give you guys, okay, I know we only have like 10 minutes. Please try it and then share your answer jalan kerja dalam WhatsApp. If you, for the rest of the class, please try it. If you have questions, please ask me within this 10 minutes of time. Is that okay? Everyone try, ni jawapan dia. Ya Allah. Okay, so this is typical of an exam question. This A to E. And I'm being serious. I'm not like just saying that so that you guys do it. Okay, so this is why I still want to do this question even though it's like the last 10 minutes of class. So please try this. Shakira, Christina, Redha, Haikal, and Fai. And I also noticed that Haikal punya nama ada tulis sebelah dia Ning. Why? Why is Haikal called Ning? Is it like Ning for Ning by Zura or what? Okay, so if that is, I already assigned, so I'm waiting for the answer on WhatsApp. Other than that, we are done with class. Okay, any other questions? No? Okay, so have a great rest of the day. Study well. All the best with your bio exam. And take care. Bye-bye.
Thank you, Doctor.
Welcome. Ambil gambar siap-siap.
Thank you, Doctor.
Thank you, Doctor.
Ambil gambar
you, Doctor.
share slide this time.
Thank you, Doctor.
Bye.
Ya, Doktor.
Welcome.
Thank you, Doctor.
Okay, bye. Nanti share jawapan tau.
Okay.
Bye. Bye everyone. Bye Nurhan, Fairuz, Fakri, Redha. Siapa yang tengah-tengah ni? Oh, tak siapa.
Thank you, Doktor.
Thank you, Doctor.
Bye. All the best.